Hello. Okay. Um, One of the main techniques you see for integration in A level is this integration by substitution. So I've got a simple example here, which we don't actually have to use substitution for, but we're going to use it to see it in action. I've got a list of things that we need to substitute on the right there. So we need to substitute the function. So it's in terms of a new letter. We'll usually use u. Uh, if we're substituting this function so that it's in terms of another letter, let's say u, then this dx doesn't work anymore because this dx means we need to integrate with respect to x. So we're also going to need to substitute the dx. The limits as well, they're in terms of x, so we will need to change those so they're in terms of u as well. So in order to do all this, we're going to start with the substitution u equals x plus 1. So this is the substitution we will use. Now we can see straight away that will allow us to substitute the function, won't it? The function that we are integrating is x plus 1 cubed, so we could just change that to u cubed. So that's why we chose that. It's a really easy substitution to make. Now, in order to find dx, we need to get a dx from our expression du equals x plus 1. And here again is another situation where dy by dx acts like a fraction. So if we differentiate this, we get du by dx because we're differentiating u with respect to x, and it becomes 1. Okay, so that rearranges to du equals dx. We multiply both sides by dx. I say it in air quotes because technically it's not a fraction and technically we're not doing that, but really we are. So that's what we get. So that's step 2 covered. We've got du equals dx. That's substituted. And now we've got to sort out the limits. So if we want the limits, the original limits are 1 and 3. So let's have a look. Let's say when x equals 3, we know that u equals x plus 1. So u equals 3 plus 1, which is 4. And when x equals 1, u equals 1 plus 1, which is 2. So they are our new limits. The x and the 3 and the 1 become 4 and 2. Okay? So now that we've done all that, I'm going to need to scroll down. So I'm just going to grab this and drag it down here. So now that we've done all that, we can rewrite this whole thing out, but with everything substituted. So we are integrating. Step 1, we substitute the function. So this x plus 1 cubed becomes u cubed. We also need to substitute the dx. So the dx becomes, in this case, dx just equals du. Normally, it'll equal something like 2 du, or it might be du over x or something. And we also need to sub the limits. So when we had x equals 3, we got 4. And when x equals 1, u equals 2. Okay? Now, that's everything done. Sometimes we'd need to do a bit more work here. Usually, we'd have to do a bit more work here. Particularly if when we found du by dx and we found dx, there might still be some x's there. We might have ended up with like x du or something. We need to substitute some more x's, but this is an integral that we can do. We learned how to do that last year. We just square brackets because we've got limits, and we add 1 to the power, divide by the new power, and we're going to evaluate that between the two limits, 2 and 4. So sub 4 in there, we get 4 to the 4 over 4, which is 64. Sub 2 into there, we get 2 to the 4 over 4, which is 4. Giving us an answer of 60. Okay. Let's look at another example. Now, when I covered the last, in the last video, I was looking at integrations that we can do by inspection. And what you'll actually find is in the textbook, a lot of the questions that are given to you, asking you to do by substitution, you can actually work them out by inspection. So here's an example of one of those sorts of questions that we looked at in the last video. Now, as I said, I recommend the way you approach this one is to first recognize that what we've got is a function of a function. Over here, we've got a function, which is x squared minus 4, and then the other function is x to the power of half. We've got a function of a function, so we might be able to do the chain rule backwards. Unfortunately, because this thing in the bracket is not linear, it's going to be difficult to do the chain rule backwards unless we've got the derivative of the bracket in front, which we do. So this is one of those cases where it's of the form derivative of the bracket multiplied by function of a function, yeah? Now, that means we can just integrate that by inspection, which if you haven't seen that video, I definitely recommend checking it out. It can cut out, if you use the techniques taught in that session, you'll be able to make a lot of these questions go a lot more quickly. However, what I want to really show here is if you found it difficult to recognize, because it's quite complicated, trying to notice that you've got the derivative of a function in front of a function of a function, you know, if you don't notice that that's the situation, it's fine. You don't have to do it by inspection. You can just integrate by substitution, okay? But let's compare it anyway and see which way is better. Anyway, so now we need to substitute everything. So the substitution we're going to use is let's use the pen. U equals x squared minus 4. The substitution will usually be given to you in the question. If the substitution is not given to you, it'll normally be relatively obvious what you should be substituting. You'll see later on in some examples that the substitution you need to make is not at all obvious, and you know it's taken mathematicians quite a lot of work to figure out that these substitutions work. Right, so so that gives us the first step. Remember, step 1 was to substitute the function. So now we've substituted the function. X squared minus 4 will just become u. Now, the thing is here, though, we've also got a 2x that we're going to have to substitute. So let's just rearrange this to make x the subject, so that if we need to substitute just an x on its own, we can do. So x squared equals u plus 4. X equals the square root of u plus 4. Now, we might not actually need to use this. It might cancel out. So we won't necessarily need to use that, but we've got it there just in case. Now we need to substitute dx. So in order to do that, we differentiate du by dx equals 2x. Now we can rearrange that to make dx the subject. So dx equals du over 2x. Now, and this is the step where the integration by inspection works. If the derivative of the bracket is in front, right, that x there is always going to cancel with this x here. You'll see it as when we work it all out. And that's why integration by inspection means we can sort of skip all this because those x's will cancel out. The other thing we need to look at is the limits. So the top limit, x equals 4. So u equals x squared minus 4, which is 12. And if x equals 3, u equals 3 squared minus 4, which is 5. So that's everything we need. We've got let's highlight everything that we need to substitute. We're going to substitute u for x squared minus 4. We're going to substitute du over 2x for the dx. And we're going to substitute the 12 and the 5. So all of those things are substituted for all of this. Oh, sorry. There isn't actually a dx on my question. But now there is. So that will be substituted as well. So all of this becomes the integral from upper limit is 12, lower limit is 5. I'm going to leave this 2x there because, as I said, it cancels. So that's u to the half du over 2x. So that 2x there cancels with that 2x. You know, this is all one, these are all being multiplied together. The du over 2x is being multiplied by all of that, so the 2x's cancel. So we've got the integral between 5 and 12 of u to the half du. And this, again, we've managed to turn a complex integral into a relatively simple one. So let's look at this. Add 1 to the power, we get u to the 3 over 2. Divide by the new power, it's 2/3, all between 5 and 12. So now we need to substitute 12 in there, so we get 2/3 times 12 to the 3 over 2 minus 2/3 times 5 to the 3 over 2. Now, looking at that, I need to square root. To get the power of 3 over 2, I need to square root, then cube. So it doesn't look like this is one I can do in my head. So we need the calculator. Okay, and that gives us an answer of 20.3. That's rounded. Okay. If you were to have done this by inspection, you would have just treated the bracket as if it was x to the half. So you'd add 1 to the power, divide by the new power, and you would have got 3 over 2 times x squared minus 4 to the, sorry, 2 over 3 times x squared minus 4 to the half, which is exactly the same as we got here, except we wouldn't have needed to change the limits because our answer would have been in terms of x. So anyway. Okay, so let's look at another example. This one, we're looking at, which one are we doing? Okay, so it's x times root x minus 2. Just checking my notes down there. Right, so this one, when we take a look at this, and we try and first decide if we can, you know, do it by inspection, we can see that we've got a bracket x minus 2 to the half, which on its own we could integrate by inspection because it's just a linear term to a power. Unfortunately, we're multiplying by x in the front, and x is not the derivative of that bracket. So unfortunately, this one we can't do by inspection. So if that x wasn't there, we would be able to do this by inspection, you know, or if this was an x squared in there, well, then the term in front would be of the right order. So it would be similar to the derivative of that bracket. So then we would be able to do by inspection. Here we can't. Notice on this case, this one is an indefinite integral. So we don't need to substitute the limits. Okay. But the difference between an indefinite integral and a definite integral is with an indefinite integral like this, you will have to sub the x back in at the end. So let's make a substitution. We're going to use u equals x minus 2. Okay. Now we need to substitute dx as well. So if we differentiate this, we get du by dx equals 1, which gives us that really easy substitution, du equals dx. The other thing, this dx, this the du isn't du over x, so that x is not going to cancel. So we are actually going to need to substitute the x as well. So let's just rearrange that. So we've got an expression for x. If u is x minus 2, x is u plus 2. Okay, so that's everything we need to sub. No need to worry about the brackets. Limits, sorry, no need to substitute the limits. So this will become the integral of, okay, so this will be root, so x is u plus 2, and u is x minus 2, so this becomes u to the half. Dx is du, so that's everything substituted. the x became u plus 2, the x minus 2 became u, and the dx became du. Okay. This that we're trying to integrate now looks kind of similar, doesn't it? It's a bracket with two terms in it, with another term outside the bracket. The thing is, though, what we've done is we've changed it so that the thing with the power of half only has one term in it. So that means we can actually expand this bracket. So if we multiply that out, we get u to the half times u, which is u to the 3/2. And then multiply by 2, we get 2u to the half. We do need brackets now because there's two terms. This is straightforward integration now. So this becomes u to the 5/2 divided by 5/2 plus this becomes u to the 3/2 divided by 3/2 and then also times by 2. So that's 4/3. And we need a plus c. We didn't need plus c in the previous two examples because they were both definite integrals. They both had powers. Now we need to substitute x back in now because we've completed the solution now. We've integrated, but look at our answer. Our answer is full of u's, whereas the original question only had x's in it, so that can't be right. Now we didn't need to sub x back in before because there were limits to put in, and we just changed the limits so they were in terms of u. So I'm going to factorize this first. And so I want to pull out as many common factors as I can here. So what we need is a common factor of 2/5 and 4/3. So 2 and 4, the common factor there is 2. And fifths and thirds, the common factor of fifths and thirds is 15. And we also need to pull out a common factor with the u's. So, you know, when you're factorizing, if you factorize x squared plus x to the 5 minus x to the 10, the common factor you pull out there is x squared because 2 is the smallest power. So that's what we do here. We pull out the u that has the smallest power. And the u with the smallest power is 3/2. Okay, so now we need to figure out what we're left with. So if we look at that first term, what do I need to multiply 2/5 by? Sorry, what do I need to multiply 2/15 by in order to get 2/5? So we need to multiply that by 3, don't we? And then u to the 3/2 times u to the 1 is u to the 5/2. Then we look at the second term there. In this second term, we want to have 4/3. Here we've got 2/15. So we're going to need to multiply it by 10. Is that right? No. 4/3. Yeah. To get the thirds on the bottom, we need to multiply by 5 and by 2. Yeah. Is that right? 10. 20/15 is 4/3. Yeah, okay. Now we can substitute the x back in. Not that x. So if we go back up, u is x minus 2. So this becomes 2/5, 15ths, x minus 2 to the 3/2 times 3 times x minus 2 plus 10. Simplify this further, we get 2/15ths, x minus 2 to 3/2. Here we've got 3x. 3x minus 6 plus 10 is 3x plus 4. Oh, plus c. Okay. So notice this question got quite complicated towards the end there. We had done the integration by substitution at this point. And it is a factor, sort of second year A level. You are sort of suddenly expected to be more confident with algebra, just basic, as in just algebra, without necessarily being taught it. So being able to factorize an awkward expression like that, you didn't really need to do last year, and now you just expected to be able to do it. So I would recommend, if you struggle to factorize that complicated expression with awkward powers, I would urge you to go and practice this. You can practice it quite a lot in your textbook if you go to the chapter on the product rule that has awkward factorizing in it. Obviously, integration by substitution, it comes up. Yeah, those chapters you get quite a lot of practice. Okay. So now we're going to have a look at certain unusual cases, different substitutions, and we're going to do it by looking at past exam questions. Okay, so as always, when we're doing an example like this, could you pause this and have a go at it, and then unpause it, and I'll work through it with you. Okay, so we've got our substitution. So u equals x plus 2 to the half. We need a du by dx, which is a half x plus 2 to the minus a half, times by the derivative of the bracket, which is 1. So in order to simplify that, we want to make dx the subject, because dx is what we're substituting. So dx equals du over a half x plus 2 to the minus a half. We can simplify this because we're dividing by a negative power, so that's the same as multiplying by the positive power, and we're dividing by a half, which is the same as multiplying by 2. So we get dx equals 2 x plus 2 to the half du. Okay. We also want to sub the limits. So when x equals 7, u equals the square root of 7 plus 2, which is 3. And then if x equals minus 1, u equals the square root of minus 1 plus 2, which is 1. So all of this, I just wanted, okay. I was trying to be crafty there, just grabbing that. There we go. So if we sub everything there, we get a new integral. So wow, I'm just pasting them everywhere. So the integral, okay, so we've got new limits. The 7 was now 3, the minus 1 is now 1. Over here on the top of that fraction, we've got x squared. Now, what is x squared when we sub it? Well, let's just leave it as x squared for now. We don't exactly know how all this is going to tidy up. But the root x plus 2 just becomes u. And then we're multiplying that by our dx, which is all this, to x plus 2 to the half du. Okay, so we're not quite done, are we? We've substituted one of the expressions that have an x in, but we've got more. Just 1 second. Okay, just had to plug my headphones in there. Right, so now we need to sub all these other x's. Now, I didn't spot it at the time, but x plus 2 to the half is u, so we can substitute that quite easily. How do we substitute the x squared? Well, let's go up here and let's look at our expression. We've got u equals root x plus 2. We want an expression for x squared, so we could square both sides. We get u squared equals x plus 2. And then x equals u squared minus 2. So x squared is u squared minus 2 all squared. Okay. So now we could get the final integrals with everything replaced with u's. 1 to 3, x squared is u squared minus 2 squared. This is over u. And this is multiplied by 2u du. Right, brilliant. Everything's got u's in it. And what we're looking for when we do the substitution with these sort of fractions, we want to go from an expression that's got a fraction on the bottom with more than one term in it to a fraction where it's the top of the fraction that has more than one term in it, because we can split those fractions up. Here, actually, we can just cancel the u's there. Brilliant. Now, what I'm also going to do, this 2 is multiplying the whole thing. I'm going to take that 2 out. Any common factor that's just a number, you can take out of the integral. So this all becomes 2 times the integral between 1 and 3 of u squared minus 2 squared du. This is straightforward-ish, so just multiply that out. We get u to the 4 minus 4u squared plus 4 du. And then we get, now we actually do the integral, we get u to the 5 over 5 minus 4/3 u cubed plus 4u between 3 and 1. Which equals 2 times, so we sub the 3 in, we get 3 to the 5 over 5 minus 4/3 times 3 cubed plus 4 times 3. And we're going to take away from that 1/5 minus 4/3 plus 4, because when we sub in 1, the u's just all become 1. Okay, and I'm going to just use a calculator. Okay. You should end up with 652 over 15. Okay, so this one's a little bit different to the other ones we've been looking at, where we're using a trig function to substitute. Please pause and have a go. The approach is the same as before. Yeah, and it's a bit unusual because there's no trigonometry in the question. But you'll see as we do the substitution why this works. Well, it's because of that 1 minus x squared. You know, if we can turn that into 1 minus cos squared or 1 minus sine squared, we can use a trig identity to turn that into one term. And a lot of the time, what we're trying to do with these substitutions is turn fractions that have more than one term on the denominator into a fraction that only has one term on the denominator. So, okay, so we've got x equals sine theta. So dx by d theta. Notice here the subject of the substitution formula is x, not theta. Again, that's a little difference before. But if we differentiate with respect to theta, we get dx by d theta equals cos theta. Rearrange that to make dx the subject, we get dx is cos theta d theta. And now we need to sub the limits. So when x equals a half, slightly awkward substitution here, that'll mean that a half equals sine theta, which means theta equals 30 degrees, but whenever we're doing integration, we have to be in radians. So that's pi over 6. If x equals 0, that means 0 equals sine theta. So theta equals 0. Okay. Now we've got everything we need to do the substitution. So let's grab the integral. And make all the substitutions. So the half becomes pi over 6. 0 becomes 0. 1 over 1 minus x squared. Okay, so let's just sub it all in. So 1 over 1 minus, and x is sine theta. So that becomes sine squared theta. All to the power 3 over 2. Now the dx becomes cos theta d theta. And that cos theta is going to cancel out. So this is the integral from 0 to pi over 6. Okay, so 1 minus sine squared is cos squared. So this becomes 1 over cos squared to the 3 over 2. And cos squared to the 3 over 2 is cos cubed. And the cos cubed cancels with the cos. To give us 1 over cos squared, which is sec squared. This is a standard integral. It's in the formula book, but it's one that I'd recommend memorizing. When we differentiate tan, we get sec squared. So when we integrate sec squared, we get tan. Okay. So sub the limits in, we get tan pi over 6 minus tan 0. Okay. Oh, I nearly. Let's write that 0 again. My hand wanted to turn that 0 into a theta. Tan 30 is one you should have memorized, but obviously reach for the calculator if you need to double check. It's 1 over root 3 minus 0. Okay, so next question. So here, the question has been broken down into 2 parts, but really, the question is just asking us to do this integral. They've just broken it down into 2 parts so they can assess how good you are at doing the substitution part of the integral, to then working with the limits and stuff. So let's do it in the 2 parts. I would normally substitute the limits right at the beginning, but because the question's structured this way, I'm going to need to mess around with it a little bit. So we've got u equals x to the half. We're going to need to substitute dx. So du by dx is a half x to the minus a half. Okay, so that means so let's do all the substitutions. We've got 1 over, right, what does x equal? So if we go back to the original substitution, x is u squared, isn't it? So that would be u squared times 1 plus root x. Root x is u. That was the substitution we're making. And du, oh, sorry, I haven't actually found dx in terms of du, have I? So from this, we get dx equals du over a half x to the minus a half, which is 2x to the half du, which is 2u du. Okay, so this is multiplied by 2u du. Look at the answer that they've got. We needed to show that we get that We do, don't we? The u is going to cancel with one of the u's on the bottom, and that gives us the integral as given. Personally, I would bring that 2 out in front of the integral sign, but obviously we have to give it in the form that they've given it to us. So hence, find the exact value of that. It's scrolling off the page, so I'm just going to grab that and reproduce it here. So we've done a lot of the work, but we do need to change the limits. So when x equals 9, remember u is root 9, and when x equals 1, u is root 1. So all of this becomes the integral from 1 to 3 of, and we can just take, we've already shown that we get that. Let's just double check that the thing they're asking us to integrate is exactly the same as the thing we messed around with in part 1, because that's 1 over x times 1. Yeah, okay. So obviously with Edexcel in particular, you do find that sometimes you're working on part 1 and then you assume part 2 just follows on from it, which it does, but it's not actually the same function. It's a related function. So we did need to double check that, but we can just write down what we've got for part 1 here. Okay, so for this one, we are going to need to use partial fractions. I'm debating whether to have a video looking at partial fractions or not. So again, if you'd like a video talking about partial fractions, let me know and I'll do one. I don't know. I feel like people often don't really need help with partial fractions, but let's see. So this is why this part is worth more marks, because we've got to use partial fractions. And in addition to having to use partial fractions, we have to figure out that we need to use partial fractions. Now, that's the thing I keep banging on about on these integration questions, is half of the battle is figuring out which approach to use. So the dead giveaway with partial fractions is that you have a denominator that's factorized into brackets. When you have a denominator factorized into brackets, usually it's going to be a partial fractions type question. Especially since we've used a substitution to get us to this point. The only other option that would be really feasible would be to do a substitution, but we've already done a substitution to get here. So okay, so we need to partial fractions here. If you've not covered partial fractions, don't worry. You can. I suspect you will have done. If you're up to integration, you've probably done partial fractions already. But if you haven't, let this be your lesson on partial fractions. It's pretty straightforward. What we can always do when we've got any sort of fraction like that, it doesn't have to just be a number on the top as well. The numerator could be u, it could be u plus 4 or something. For it to be a proper fraction, the order of the top needs to be lower than the order of the denominator, though. So if we had a u cubed on the top, it would be a slightly more awkward one to write in partial fractions. But any fraction that's written like that can be written as a number over the first factor on the denominator plus another number over that second factor. So because all fractions can be written like that, we just say it's going to be a over u plus b over 1 plus u. Now, think about fractions, right? And think about starting with this right-hand side. If I had to add 2 fractions, what would I do? Well, I'd need to get a common denominator, wouldn't I? What would that common denominator be? It would be u times 1 plus u. So it does make sense, doesn't it, that those 2 sides are equivalent. What's maybe not completely obvious is that there will just be a number on the top of both, and that's true even if this numerator had u's in it. Right. So what we need to do now, notice I've used the identity symbol rather than the mere equals symbol. So that means this is always true no matter what u is. So in order to work out what a and b are, we're going to multiply this whole equation by u times 1 plus u. Okay, so if I multiply the left-hand side by u times 1 plus u, it cancels and we're just left with 2. If I multiply the right-hand side by u times 1 plus u, well, this first term, multiply that by u times 1 plus u, the u will cancel and we're left with a times 1 plus u. Then if I multiply this by u1 plus u, if I multiply it by that, the 1 plus u part cancels and we're just left with bu. Okay, now we're going to sub in different values of u in order to find out what a and b are. Because this is true, valid for all values of u, we can just make u equal something. Now let's make u equal a value that makes one of these a or b disappear, because that's going to be the easiest way to do this. Let's make that b disappear by making u equal to 0. So if u equals 0, the left-hand side will still be 2, and the right-hand side will be a times 1 plus 0, so that'll just be a. So we've got to a sorted. Now if we let u equal minus 1, because that makes a disappear, we get 2 equals a disappears, so it'll be minus b, which means b equals minus 2. Okay, so now that integral that we started with, that equals the integral from 3 to 1 of a over u, so that's 2 over u, plus b, which is minus 2, over 1 plus u. Okay. We can sub in the limits once we've integrated. So 2 over u becomes 2 log u. 2 over 1 plus u becomes 2 log 1 plus u. And that's going to be between 1 and 3. So this becomes 2 log 3 minus 2 log 4 minus 2 log 1 minus 2 log 2. So that all becomes, let's take out 2 as a factor, and we get log 3 minus log 4 plus log 2. Using our laws of logarithms, that becomes 2 log, we've got to do, okay, so we're doing 3 plus 2, which is, when you log them, that's multiplying, so it'll be 6 divided by 4, so it'll be 6 over 4, which is 3 over 2. Okay, next question. Very similar to the previous one, we're first going to do the substitution to transform it, and then actually work out the value. So again, please pause and have a go at this. Okay, so for part 1, we're dealing with u equals e to the x plus 1. So let's differentiate du by dx. It's just e to the x, which means dx equals du over e to the x. Okay. So let's try and do the substitution. Integral between integral of e to the 2x over e to the x plus 1 dx. Okay, so let's sub everything in. Okay, so the e to the 2x, well, in order to get e to the 2x, we need to use this. So e to the x equals u minus 1. So e to the 2x is that squared. Remember, we need to square e to the x to get e to the 2x. So that becomes u minus 1 squared. And then the bottom is e to the x plus 1, which is just the u that we used. And then we've got du over e to the x. Now that that e to the x we need to substitute as well. So this will become u minus 1 squared over u du over, and e to the x is u minus 1. Now, we've got a u minus 1 on the bottom, we've got a u minus 1 on the top, so they cancel. And we're left with the integral of u minus 1 over u du. Now, what did we have to get? Yeah, that was the point we had to get to. So that's it. Now, I'm scrolling down a bit, so I'll just grab this. For part 2. Okay. So we need to sub the limits. So when x equals 1, what was our sub? U will equal e to the 1 plus 1. And when x equals 0, u equals e to the 0 plus 1. E to 0 is 1, so that becomes 2. So we get a weird limit now. So this becomes the integral from 2 to e plus 1 of, now we've got e to the 2x over e to the x plus 1. We've already transformed that, so we can just change that into u minus 1 over u du. Now here's the point of changing a fraction so that has two terms in the top is so that we can split it, so it becomes u over u minus 1 over u. So it becomes the integral between 2 and e plus 1 of 1 minus 1 over u, which is u minus log u between 2 and e plus 1. So subbing e plus 1, we get e plus 1 minus log of e plus 1. Take away 2 minus log 2. Now, they actually gave us the answer, sort of. Yeah, they gave us the full answer. So shall I grab that as well so we can check our answer conforms to the answer they gave us? Let's just keep an eye on that. That's what we're wanting to attain over here. Let's see if we can make that look like what that does. It does very quickly actually, because if we collect, we've got e plus 1 minus 2 there, so that becomes e minus 1, and then we have minus log e plus 1 minus minus log 2. Okay, now I would tend to write that as log 2 minus log e plus 1. However, they want yeah, so we want to have the e plus 1 on the top of the bracket. So let's just write that as e minus 1 minus log e plus 1 minus log 2. Let's write it slightly weirdly like that in brackets, because when we combine those two logs using the division laws of logs, we just get e plus 1 over 2. So that becomes e minus 1 minus log of e plus 1 over 2 as required. Okay. Next question. Again, they're not giving us, this time they're not giving us any help, like breaking it down into stages. So pause the video and have a go at this. Okay, so we're going to need to substitute the dx. So dx by d theta is sec squared theta. So dx equals sec squared theta d theta. And we also need to sub the limits. So when x equals root 3, that means root 3 equals tan theta. Okay, so theta is pi over 3. It's one you meant to have memorized. 60 degrees gives you tan theta is root 3. And if x is 1, oops, another one you should know, 45 degrees. Okay. So let's take the integral and sub everything. Okay, so the limits, they turn into pi over 3 at the top, pi over 4 at the bottom. 1 minus x squared. So x is tan theta, so this will become 1 minus tan squared over 1 plus tan squared. And dx turns into sec squared theta d theta. Okay, so there's a lot going on there, and it doesn't really seem like we've simplified it very much. But we're going to need to use a trig identity here. Okay. So the trig identities that we're interested in are you probably learned them quite recently, I would have thought, if you've covered the second year trig. So let's just remind ourselves what they all are. Sine squared theta plus cos squared theta equals 1. Yeah. And if we divide all of that by cos squared, we get tan squared theta plus 1 equals sec squared theta. And, well, actually, that's the identity we will want, isn't it? However, let's just write the other one as well, just so that we've got them. Cot squared theta plus 1 equals cosec. So these need to be memorized. Hopefully you've memorized the top one, but the others need to be memorized so that you can recognize them when they come up. So notice what have we got there then? Well, actually, we've got a tan squared plus 1 on the bottom and sec squared on the top. Tan squared plus 1 is sec squared, so we can just cancel them. Okay. Now, we could integrate tan squared, but the standard integral that we know is about sec squared, isn't it? We know that sec squared integrates to tan. So let's change the tan squared using, again, this one to sec squared minus 1. Okay? So that whole thing then becomes the integral from pi over 4 to pi over 3. 1 minus sec squared minus 1 d theta. And the whole thing is multiplied by d theta. That's 1 minus minus 1. So that becomes pi over 3, pi over 4. 1 minus minus 1 is 2 minus sec squared. So now we can integrate. 2 becomes 2 theta. Sec squared becomes tan. That is between pi over 4, pi over 3. Sub in pi over 3, we get 2 pi over 3 minus tan of pi over 3, which I think we worked out before. If we couldn't quite remember, it's root 3. Take away 2 pi over 4 minus tan of pi over 4, which is 1. Okay, so simplifying that, we've got 2 pi over 3 minus pi over 2. Okay, so that's 4 pi over 6 minus 3 pi over 6. So that's pi over 6 minus root 3 plus 1. And finally, pause the video and have a go at this one. Okay, so differentiate our u, we get du by dt. Slightly awkward, there's no x's here, so if we differentiate that with respect to t, we get 1 over t. And we're wanting to substitute dt. So dt equals t du. Okay. Then the limits. Well, when t, I keep wanting to write x. When t equals e, u equals 2 plus log e, which is 2. When t equals 1, u equals 2 plus log 1, which is 2 as well. Log e is 1. Yeah, I got that one wrong. Log e is 1, so 2 plus 1 is 3. So the limits are 3 and 2, not 2 and 2. So then the whole integral then becomes, let's sub the limits first. We get integral between 3 and 2 of 1 over, okay, so we've got to sub the function. So u equals 2 plus log t. I'm going to leave that t there because what we've got going on here, that t there is going to cancel with the t in the t du. So I'm not going to bother changing those in terms of u. So this becomes t times 2 plus log t, that's our u, squared, and dt is t du. So the t's cancel. So that equals the integral of, it's just 1 over u squared, so u to the minus 2 du between 2 and 3, which is add 1 to the power, divide by the power, between 2 and 3. So that becomes minus 3 to the minus 1, minus 2 to the minus 1. So we've got to be slightly careful with all these minuses. 3 to the minus 1 is a third, so this is minus a third plus a half. Yeah, so, and a half minus a third is 3/6 minus 2/6. So that's 1/6. So that's it for this. There are tons more, examples for you to practice with slightly different substitutions that are used and stuff. I will be going through many more examples like these in the final video in the integration series, where I am going to work through lots and lots of exam questions for you. If you've got any questions about anything that's come up on this video, or if there's any integration question you would like help with, put it in the comments and I will answer your question there. So see you later. Join us for the next video on integration by parts.